chlorine gas. Now, because the electrons are attracted to both nuclei in the molecule, they actually spend the majority of their time in the space between them. This is often described as sharing electrons, and we call this kind of bond a covalent bond. But not all sharing is equal. As you know, I have an older brother. The strength with which an atom holds shared electrons is called its electronegativity. The electronegativity of various elements are all super well known and waiting for you in tables on the internet. If two atoms in a bond have very different electronegativities, like say hydrogen at 2.1 and oxygen at 3.5, the electrons are more attracted to the atom with the higher electronegativity. The difference is so great that the electrons spend most of their time around the stronger atom and much less time around the other one. Like how all of the neighborhood kids wanted to hang out with John, my older brother, because he was more charismatic. When the electrons hang out closer to one side of the bond, it creates a slight negative charge in that area and a slight positive charge around the other atom. This separation of charges is called polarity. And it's the polarity of the molecule that these atoms form, H2O, that makes water the most important molecule on Earth. Covalent bonds like this, where electrons are attracted to one atom more than the other, causing a separation of charges, are called polar covalent bonds. But when a covalent bond forms between two identical atoms, like the two chlorine atoms in our graph earlier, the electrons are distributed evenly. We call this a nonpolar covalent bond. But you've also got to consider the middle option, where the atoms aren't identical but have very similar electronegativities, like hydrogen with an electronegativity of 2.1 and sulfur at 2.5. The difference here is so tiny that the electrons are pretty much still evenly distributed, and we call that a nonpolar covalent bond as well. There's a huge world of important chemicals that have these kinds of bonds, so many in fact that we will dedicate a couple of separate episodes to them. Covalent bonds tend to form from nonmetals and sometimes metalloids, those elements that have both metallic and non-metallic characteristics. That's because most of them hold their electrons so tightly that they're more likely to share them with another atom than to gain or lose them altogether. Metals, on the other hand, have loosely held outer electron shells, so they're constantly dropping electrons and becoming positive ions. And when positive ions come across negative ions, like those formed from halogens, for instance, you have to know what's going to happen. They're attracted to each other, which means energy is required to keep them apart, which means that they're gonna bond if they can, creating that oh-so-wonderful point of minimum energy. This type of bond is unsurprisingly called an ionic bond, a bond formed between a positive ion and a negative ion. Because the ions are formed when one atom loses electrons and the other gains them, we often say that an ionic bond is formed by the transfer of electrons from one atom to another. Particles' ionic bonds are extremely polar, way more polar than polar covalent bonds. And so those are our three types of bonds. Nonpolar covalent, formed by the equal or nearly equal sharing of two electrons between nonmetal or metalloid atoms. Polar covalent, formed by the uneven sharing of electrons between two nonmetals or metalloids. And ionic, formed by the transfer of electrons from a metal to a nonmetal. It's important to remember, though, that there aren't only three designations for chemical bonds. Just like human relationships, bonds don't always have really well-defined boundaries. Everything is a continuum. Labels are useful, but they can only take us so far. There are, however, certain properties that each kind of bond tends to have that you should know. For instance, ionic compounds are often crystalline in their solid form because of the way the ions pack together, like salt is. They're generally soluble in water because the two ions interact separately with the positively and negatively charged areas on a water molecule, and once they're separated or dissolved, the ions allow the solution to conduct electricity. Covalent compounds, on the other hand, tend to be softer solids, liquids, or gases like Cl2 is at room temperature. They're often not soluble in water, and even when they are, the solutions don't conduct electricity. The difference in these properties stem mostly from the differences in their polarities. So yeah, polarity is crazy important. A Lewis structure is a two-dimensional model that represents covalent bonds as straight lines and unbonded valence electrons, those in the outermost energy level of an atom, as dots. Inner electrons aren't shown at all, and although it was developed to explain covalent bonds, it also works for ionic bonds. In Lewis structures, bonds are formed by pairs of valence electrons called bonding pairs in the space between two atoms. Pairs of electrons that are attached to only one atom are known as lone pairs. As you probably remember, atoms are most stable when their outermost electron shells are filled. For many atoms, that takes 8 electrons, so it's called the octet rule. And if you're bracing yourselves for some exceptions to this rule, well, you are correct. Tiny little hydrogen can only hold 2 electrons total, not 8. That'll make more sense when you watch our upcoming episode about atomic orbitals. But also elements in the third row of the periodic table and below often have more than 8 valence electrons. Beryllium and boron are notorious for having weird numbers, like 6 or 12 electrons. So yeah, the whole octet thing is really more of a gentle nudge than a rule. Let's stick to rows 1 and 2 of the table to keep it simple. First, figure out how many total valence electrons are available. It doesn't matter which atoms they come from or how they're arranged changed before you start. Each hydrogen atom has 1 valence electron, and oxygen has 6 for a total of 8 electrons. Neither hydrogen nor oxygen has enough valence electrons to be stable, so they share electrons to make up the lack. And just like how sharing a snack can make a new friend, the sharing creates a bond between the atoms. Lay out the molecules and create the bonds. Both hydrogens are bound to oxygen, so the oxygen goes in the middle. Remember, in Lewis's model, each bond requires a pair of electrons. So we used 4 of the 8 available electrons to form the bonds. Now fill in the outermost energy levels. Hydrogen atoms only need 2 electrons total, so they're already full. Oxygen, on the other hand, needs an octet, 8 electrons. So place the remaining electrons around it in pairs to complete the structure. Finally, again, Lewis structures use lines to represent covalent bonds, so put those in the place of the bonding electrons, and you have it. Water contains 2 covalent bonds and 2 lone pairs. Simple enough. Well, it can get a little trickier. Let's do carbon dioxide, another tremendously important molecule on our planet. Carbon has 4 valence electrons, and each oxygen has 6 for a total of 16 electrons. Both oxygens bond to the carbon, so put the carbon in the middle and make the bonds using 4 of the 16 electrons. All 3 of these atoms, they need a full octet, so fill that in next. So yay, now all the atoms have a full octet, but take a closer look. 20 electrons are needed to fill the octet, but only 16 are available, so what to do? When there aren't enough electrons to fill all the octets with normal sharing, atoms have to share more of them. In this case, they form a double bond by putting 2 pairs of electrons, for a total of 4, between each pair of atoms. All 4 bonding electrons count toward both atoms' octets, so we need fewer lone pairs to fill all the octets. The double bonds allow us to use only 16 electrons. Replace the bonds with double lines, and the Lewis structure is complete, with 2 double bonds and 2 lone pairs on each oxygen. That was a little weird, so surely we could do something simple like molecular nitrogen, just 2 atoms of nitrogen bonded together, right? Well, nitrogen has 5 valence electrons, and there are 2 atoms, so that's a total of 10 electrons. Let's put in the bond and complete the octets, and we've used 14 electrons. We don't have that many. We could try a double bond, but that still uses 12 electrons, 2 more than we got, so we still don't have enough electrons to go around. Let's kick it up 1 more notch and make it a triple bond. That's when atoms share 3 pairs of electrons. And that does it, just 10 electrons and all the atoms have a full octet. Switch the lines to bonds and it's done. A triple bond and a lone pair on each atom. And this is why molecular nitrogen is really hard to break up to form like fertilizer and stuff. In case you're wondering, 3 is the maximum number of bonds. There is no such thing as a quadruple covalent bond.